Hello, this is Ahmed Al Hadrami. This presentation is for course ME 496, video assignment 3. Our problem statement states, in the system, water is pumped from tank 1 to tank 2 through 1500 feet of cast iron pipe with a diameter of 8 inches at 360 feet cubed per minute. The exit from tank 1 and entrance in tank 2 are both sharp-edged, and both elbows are regular radius threaded. If Z2 equals 225 feet, measured from the same reference datum for Z1, calculate the power that the pump delivers to the fluid. Our problem statement here wants us to calculate the power that our pump delivers to the fluid. How do we calculate the power? First, let's examine our problem diagram and let's understand what is going on. We have a tank on one side of the system and another tank on the other side of the system. Both tanks are interconnected by a 1,500 feet of cast iron pipe. In between, there is a centrifugal pump that pumps our fluid, in our case the water. It lifts the water to the desired location. We know that we are dealing with a pump, and our problem statement wants us to find the power that our pump delivers to the fluid. Since we are dealing with a pump, we have to understand the performance characteristics of our special device, the pump. The performance of our pump is given by the equation density times gravity head gain. We can see that this is our specific weight. The solution to this problem statement would be the answer to the performance equation, which will give us the power of the pump delivered to the fluid. Looking at our equation, we know the specific weight of water. We are given the volumetric flow rate. However, it is per minute. We are going to have to change our units to per second. Let's go back to our diagram one more time and follow the direction of our flow from tank 1 to tank 2. Our flow enters the sharp-edged entrance from tank 1, and it is affected by the sharp edge. We will go into this with more details in a moment. So the velocity profile here is building up, reaches here, it is fully developed. It enters our centrifugal pump. Our centrifugal pump creates a centrifugal force. This centrifugal force creates an increase in the velocity of the fluid. This increase of the velocity of the fluid causes an increase in the kinetic energy, which is then transformed to pressure. Inside our pump, we have an impeller. Our impeller is the cause of our mechanical energy. Our mechanical energy that is being transferred to the fluid by the impeller is inside our pump. So what the impeller does is it catches the water from the suction, catches the water through its veins, and as it is rotating, it picks up the fluid and discharges it on the other side of the pump. Our water keeps flowing, hits our first elbow bend. At our first elbow bend, we will have a redirection of our flow. So something important that we will discuss in a moment is going on here. Also at our second elbow bend, there is another redirection, a 90-degree redirection. Our flow continues and then exits the sharp edge to our tank. Let's start by noting down our givens in the problem. We are given the length of the pipe, we are given the diameter of the pipe, (8 inches), converted to feet to stay consistent with our units, and we are also given our volumetric flow rate, 360 feet cubed per minute. However, our standard units for the volumetric flow rate is per second. So this comes out to 6 feet cubed per second. We are also given the exit from tank 1 and entrance in tank 2 are both sharp-edged. And the elbow bends are regular threaded, regular radius. Thread. By noting down our givens, we can determine what are the values that are missing in the equations we are using for the principle we are applying. We have concluded that our answer to this problem statement would be the value to our performance equation for the pump. We have said that we know the value of the specific weight of water. We are given the volumetric flow rate, and the head gain of the pump is what we are interested in. It it is very important to understand what is the head gain of the pump. We will go into more details in a moment. We can start by calculating our velocity, since we can use the continuity principle. The continuity principle is one of the fundamental principles used in the analysis of flow. Before solving for the velocity, I would like to introduce the most important equation we have learned, is the Bernoulli's equation. We have said that we are interested in the head gain of the pump. The head gain of the pump is the height at which a pump can raise water. In other words, the discharge head of our pump is just a measure of the power of a pump. So now that we understand the head gain of our pump, and we know that to solve for velocity or pressure in any incompressible fluid at a steady state, we can use the Bernoulli's equation. But in this case, we have our head gain, and then we have our head losses due to the bends and due to the sharp edges. By introducing the Bernoulli equation that takes into account the head gain and the head loss due to the flow of our fluid through the straight pipes and the bends, our energy equation is the following. Head of the pump, and if we had a turbine, extraction of turbine, it would also be considered. Plus our head losses. We can think of this as the energy in equals the energy out. Just like any system, whatever comes in equals what comes out. It is important to understand each and every term in the Bernoulli's equation, because we are going to identify two locations before applying it. Recall that pressure, velocity, and height have to be at each of these locations that we pick in our system. So I would pick our first location to be at our atmosphere, because we know the pressure at this point, the velocity, and the height. And same for our second location. We select the location in such a way as to be able to specify as much information as possible, or the maximum information possible. This in mind, we have said location 1 is at the top of our liquid open to the atmosphere, and location 2 is also open to the atmosphere. We can determine that our velocities, our pressure goes to 0 because it is open to the atmosphere. And we do not have a turbine in our system, so the head extraction goes away. We are left with our velocities. We did assume for the Bernoulli's equation that our fluid is incompressible. It is at steady state. So, as we said earlier, it is very important for us to solve for the head gain of our pump. And to solve for our head gain, we need to know the values for V1 and V2, Z1 and Z2, which are given to us. And HP is an unknown, and our head losses are unknowns. So keep in mind that our head losses include our minor head losses and major head losses. We will break it down in the next steps. From the continuity equation, we know that Q1 equals Q2. Therefore, VA equals A2. However, our areas do not change throughout the system. Therefore, V1 equals V2. So our velocity terms will cancel out. We also know that we have a flow that is developing at the entrance region, and then it gets fully developed into the straighter section of the pipe. We will go into more depth on the velocity profile in the entrance of tank 1. So in a fully developed flow, the velocity does not change between section 1 and section 2, since the frictional forces or the viscous effects have already done what they can do. So for a fully developed flow, we know that our velocities will not change between section 1 and section 2. Solving for HP, we are left with Z2 minus Z1 plus HL we know Z2 and we know Z1. However, as we just said, this head loss term includes the head loss minor and the head loss major. our HP value, or the head gain of our pump, can be calculated via this equation that considers the energies in our system. In order to solve for the head gain of the pump, we need to solve for the head loss of our major head loss of the pump. Our major head loss of the pump is found by the Darcy's equation for head loss. We will mention the difference between the head loss, the major head loss, and the minor head loss. First, we will start by our major head loss. It is given by the Darcy's equation, or frictional factor, multiplied by our length over the diameter square over 2g. Our F value is our frictional factor. Our length is the length of our pipe. Our diameter is our inner pipe diameter. Our velocity term is the fluid velocity, which we will determine 2 times the gravity. The major head loss is because of the friction between the fluids and the walls of the pipe. The viscous effects are the main cause for our head loss in our major head loss. Whereas our minor head loss considers the head loss in various pipe components, such as valves, bends, elbow bends, sharp edges, considering the loss coefficient. Our minor loss considers the loss coefficient in those different pipe components. When there is a redirection of flow, there is a coefficient of loss. We can have more than one component in our system, so we can sum the coefficient of loss. (2g) squared. Our frictional factor is a value that depends on our Reynolds number and our relative roughness. Depends on relative roughness and our Reynolds number. So before being able to solve the problem, we are required to find the Reynolds number and the relative roughness, so we can determine the frictional factor. Let's go back to our head losses equations. We have just discussed how we are going to determine our frictional factor. We know the length of our pipe is given to us. The diameter is given to us. The velocity is something we have to consider. and calculate. 2 times the gravity is a known value. It's a constant. And for our head loss in our minor, our KL, as we said, it is our coefficient of loss for each individual component. Will have its own coefficient of loss. We will determine the coefficient of loss present in our tank 1 entrance and our first bent, our second bent, and our sharp-edged exit. All will be considered since they are components of a pipe. And in determining the frictional factor, since it is dependent on the relative roughness and Reynolds number, we are going to have to calculate our Reynolds number. And the sequence of steps is important when solving this problem, because to find the Reynolds number, we first find the flow velocity, because we know the equation for Reynolds number is the velocity times density over the kinematic viscosity. This is our fluid velocity, a diameter of our inner pipe, internal pipe diameter, and our kinematic viscosity. We know from the continuity of flow that Q equals VA, so V equals Q over A. We are given our volumetric flow rate as 360 feet cubed, and we have converted it to be per second, feet cubed per second, and that is 6 feet over our area, our cross-sectional area that is perpendicular to the flow is pi d squared over 4. Our diameter is 8 or 12 squared. Our velocity comes out to 17.189. It is very important to note down our fluid velocity. Now that we know our fluid velocity, we can determine our Reynolds number. The importance for calculating Reynolds number is because we can determine if it is laminar or turbulent flow. Our velocity is 17.189 feet per second times the diameter, also in feet, over our kinematic viscosity found in the table. Our Reynolds number comes out to 94 7 0 3 7 3 4. Our Reynolds number is too large for our system to be, for our flow to be laminar. Our Reynolds number is greater than 2000. That means we have a turbulent flow. We're dealing with a turbulent flow. Now that we have determined that our flow is turbulent flow and we know our Reynolds number, we can go ahead and find our frictional factor. Our frictional factor depends on the relative roughness and Reynolds number. So the frictional factor number is found in Moody's chart. Since we are dealing with turbulent flow, the determination of the frictional factor will be via the equation or the formula known as Colebrook formula. The disadvantage of this formula is that it uses implicit solutions because it is implicit in the dependence of the frictional factor. And this requires differential equations, knowledge of differential equations to solve for the frictional factor. However, a 10% accuracy is expected in fluid mechanics. Therefore, it is possible to use an equation or a formula that approximates the Colebrook value or the Moody chart, the frictional factor from the Moody chart value, without an iterative method. This equation that is found in our book is given by natural log of the roughness with the diameter over 3.7 we have calculated our Reynolds number. We know our roughness number could be tabulated from our book, and our value for the roughness is 0.00085 and the diameter is given to us. Therefore, we can solve for our frictional factor. I have done the math in advance so we can save time. Our frictional factor comes out to be 0.0218. To double check my frictional factor, I have used a website that can determine the frictional factor by providing the website my Reynolds number and my relative roughness number. This value is also a very important value in our solution. Now that we have determined our fluid velocity via the continuity principle and our Reynolds number that helped us in finding the frictional factor, we can solve for our head loss in the major cases. Plugging in our values, squared over 2 times 32.2. My major head loss comes out to be 217.978 feet. And my minor head loss is going to be considering all of the loss coefficients of our different pipe components. So for our entrance at the gate tank entrance, our loss coefficient is 0.5. At the bend, it is 1.5. The second bend, it is also 1.5. And at the exit, it is 1. These loss coefficients could be tabulated from our book. And this comes out to this value comes out to 20.644 feet. The major head loss and minor head loss are very important values, since they are the energy lost in our system. We know that energy in equals energy out, and we know that this is our head losses. So our head gain is equal to our head losses, not by value, but they are equal as in they cancel out. The energies cancel out. The energy in cancels the energy out. Moving on, now we are ready to use our equation, the Bernoulli equation, that has been simplified to this form and further to this form. We are ready to use this equation. And I'm out of space. So our head gain is equal to our height 2 minus our height 1 plus our head loss, that's major, plus our head loss, that's minor. Those values were given to us, and our major head loss calculated as 217.978 feet plus our minor loss 20.644 feet. Our head gain of the pump adds up to 363.649 feet. This is the power of our pump. Our pump can raise water up to this height. Now that we have calculated our head gain, it is just a plug and chug step to calculate the performance of our pump. As we stated earlier, that our performance could be found using our pump performance equation. Our specific weight of water is a value that can be calculated, that can be found in the table in the book. In the case that we are dealing with a different fluid, which is not water, we would have to find the specific weight of that fluid we are working with. Specific weight of water is 62.4. And our volumetric flow rate is 6 feet per second, cubed per second. And our head gain is 363.649 feet. This value comes out to 47 horsepower. And it is important to note that our units that we are left with are lb per feet second. So the traditional units for pump performances are horsepower. So we would like to convert our value to horsepower. We know 1 horsepower equals 550 lb per feet per second. So converting this to horsepower, and we come with the power of the pump to be 247.34. This is the performance for our pump. This is the power that our pump delivers to our fluid. I hope this is a clear view for the problem. So we will go over it again, step by step. I hope I covered everything. We did say that our problem statement wanted us to determine the power delivered by the pump. and we have found the power by using the performance for the pump equation. We are missing an unknown value, which was the head gain, and the head gain is nothing but the height at which a pump can raise water. So it is the measure of the power of our pump. And after knowing the issue that is stopping us from calculating the performance, we went ahead and tried to solve for the head gain of the pump. We said that the head gain of the pump is calculated using the Bernoulli equation that considers the head losses and the head gains. And we wrote our Bernoulli equation. And then we have identified our two locations in our system. Those two locations are selected in such a way as to be able to specify the maximum information required. So we can know the atmospheric pressure, we know the height at this point, and we know the velocity. Same as for location 2. After that, we have simplified our Bernoulli equation. We have said that our velocity does not change between section 1 and section 2. And we have proved it using the continuity equation. We are left with HP equals this whole term. This whole term got broken down more clearly. Our head loss contains a major head loss and a minor head loss. The major head loss is because of the viscous effects on the wall and on the wall in a straight pipe. And for our minor losses, our head loss is due to the different pipe components in our system. After determining the head losses, the major and the minor, we were able to solve for our head gain. And from there, we just plugged our head gain of the pump value into the performance equation, and we have concluded that the power delivered is 247.34 horsepower. I hope I covered everything. Also, it is important to determine the Reynolds number, because it is what tells us if our flow is turbulent or laminar. And because we know it's a turbulent flow, we know finding the frictional factor would depend on the Reynolds number and the relative roughness. The relative roughness is considered into account when we are dealing with a turbulent flow. Because in a laminar flow, the roughness of the pipe wall will be very thin, it is insignificant. And to discuss a little more about what I have promised, in this region, our tank, this is our tank. Our flow comes into this direction. As it enters, the flow is redirected because of those sharp edges. And whenever there is a redirection of flow, the redirection of flow changes the behavior in our system. As it enters the flow, it is known that there is an entrance region and there is a fully developed region. Now, in the entrance region, the velocity profile is changing in the axial direction. So if we would draw, it is changing in the axial direction until it reaches the fully developed area where our velocity reaches a constant value and here the velocity is constant in the axial direction. We also did forget to mention that we have a very important region in this area. This region, or this zone, consists of 3 different regions. We have the top boundary layer, bottom boundary layer, and the in-between flow. This region, or this zone, is known as the vena contracta region. And I hope I covered everything. For confirmation, this is Ahmed Al-Hadrami.